In physics, impulse is defined as the change in momentum of an object when a force is applied to it over a period of time. And we can represent this mathematically as J is equal to the change in momentum, which is equal to the force applied to an object over some time period. And if we expand out this change in momentum term, remember momentum is mass times the velocity of the object, we get mass times the final velocity of the object minus the mass of the object times the initial velocity equals the force applied to the object over some time period. And the change in momentum is simply the difference in the object's initial and final momentum. So this expression here is called the impulse momentum theorem. And it shows us that a small force acting over a large time period can produce the same change in momentum as a large force acting over a short time period. So for example, if we have an object in its initial state and a small force is applied to this object over a long period of time, and this is the final state, this is the initial momentum, and this is the final momentum, we can create the same change in momentum here on the same object by using a large force over a very short period of time. Now this principle here helps us analyse collisions and impacts, and we can rearrange this equation up here to make the force the subject of the equation. And when we do this, we can start to see how the change in time and the force on the object relate to one another. So we know that the change in momentum of an object is equal to the force applied to the object multiplied by some time period. And if we divide both sides by delta t, our force is equal to the change in momentum divided by the change in time, which is equal to the mass of the object multiplied by the difference in the final speed to the initial speed over the change in time that the force is applied to the object. So let's clarify this a bit further with an example problem. So in our problem, we have a 1,000 kilogram car moving westward at 12 meters per second, and it collides with a large oak tree, which brings it to rest in 0.25 seconds. So our goal here is to find the force exerted on the car during the collision. So our car initially is moving to the west at a velocity, initial velocity of 12 meters per second. In its final state, its velocity is 0 meters per second. So we know the mass of the car, which is 1,000 kilograms. We know the final velocity, which is 0 meters per second. We know the initial velocity, which is 12 meters per second, and we know the time it takes to slow down from 12 meters per second to 0 meters per second, which is 0.25 seconds. Now, because we're dealing with vectors here, for example, the force is a vector, the momentum is a vector, and these velocities are vectors, we need to create a simple convention that will describe which direction is positive and which direction is negative. So our initial velocity is at 12 meters per second, and we're going to make this west direction the positive direction. So west is positive. And we're going to say east is negative. So our velocity vector has a positive value, our initial velocity. Now, which direction would our force need to act in order to stop our car's motion? So would it be pointing towards the east and be negative, or would the force point towards the west and be positive? It would have to point towards the east in order to slow this car down, because it needs to push against the car's motion. So when we calculate everything in a minute, we should get a negative value for the force, and the negative sign, simply tells us which direction the force is acting on our car. So let's add in our values. So our force is equal to the change in momentum, which equals the mass, 1,000 kilograms, of our object, multiplied by the difference in the velocity. So the final velocity is 0 meters per second, minus 12 meters per second, that's the initial velocity, divided by the change in time, which is 0.25 seconds. This equals a negative 12,000 kilograms meters per second divided by 0.25 seconds. And we get a force of negative 48,000 newtons, or negative 4.8 times 10 to the 4 newtons. And this is the amount of force required to stop this car in 0.25 seconds when it's travelling at a speed of 12 meters per second. Now imagine the car misses the tree and instead drives into a field of corn and comes to rest in 10 seconds. So our delta t now, instead of being 0.25 seconds, it's increased to 10 seconds. What is the resultant force on the car in this scenario? So do you think the force would be greater than 48,000 newtons, the same, or lower than 48,000 newtons? So we have a very similar scenario here. The only difference is the amount of time it takes the car to come to rest. So if we plug in some numbers again to find out what this force is, we've got 1,000 kilograms for the car, multiplied by its final velocity, 0 meters per second, minus its initial velocity at 12 meters per second, divided by the change in time, 10 seconds, we have negative 12,000 kilograms meters per second. So the change in momentum is the same as the last scenario, but the length of time that this constant force is acting on the car has increased. We get a force value of negative 1,200 newtons. So our constant force slowing down our car is far lower now, which means that there's far less force exerted on the car and its passengers during this collision. So when dealing with collisions involving the human body, it's vital that we try and increase this amount of time here, because this reduces the resultant force. So for example, if you have a diver jumping from a 10-meter platform, this diver always lands in water rather than on solid ground. The water increases the collision time and therefore massively reduces the force exerted on the diver's body. And that's why the diver can survive a 10-meter fall into water.